is 40 Days of Chemistry, Part 17. This time looking at 9.6.5 and 9.6.6, Ocean Chemistry and Deep Ocean Corrosion. Two factors in the ocean that change as you increase your depth are temperature and pressure. This graph on the left here shows you how pressure changes in the deep ocean. As you go down in depth, or as you increase your depth, the pressure increases, the water pressure increases, and that's because of all the extra water on top of where you are pressing down. In addition, the temperature decreases as your depth increases, dropping down to less than 5 degrees at about a kilometre. And the reason why the temperature drops is because you've got less light energy taking energy into the water, because it only penetrates about 150 metres, and also there's slow transport of heat in the water from the surface to the deep ocean. And one thing to remember about this temperature is that lower temperatures means particles have lower energy, and that means there's less particles with energy greater than the activation energy of any particular reaction. The next thing we're looking at is salt in the ocean. Now, salt solubility is relatively unaffected by pressure, but salt solubility increases with increasing temperature. And there's a graph here showing solubility of some salts as temperature increases. As you can see, all these salt solubility increases with increasing temperature. But looking at sodium chloride here, we can see that between 0 and 120 degrees, its solubility hardly changes at all. And that's why you get a profile of this for salt in the ocean. Even though the temperature does drop, and therefore the salt solubility does decrease a little bit, it's not very much. It goes from about 35.5% weight percent to 34.5% weight percent. So there is pretty much consistent or constant salt concentration in the deep ocean. There is a tiny little bit less in the deep ocean, but overall there's not much difference in salt concentration from surface to deep ocean. And let's look at gases in the ocean now. First of all, the main gases we're going to look at are oxygen, nitrogen and carbon dioxide. And we know in the atmosphere that nitrogen makes up about 78% or 80% of the atmosphere, oxygen about 20%, and the carbon dioxide concentration is a very, very, very small percentage indeed. But then you look at the concentration in the ocean, and it's quite clear that even though oxygen and nitrogen are high percentages in the atmosphere, they're around 10 to 20 parts per million only in the ocean, whereas carbon dioxide, which only makes a tiny fraction of the atmosphere, is up around 100, up to 100 parts per million. Based on the graph down below, it's about 50 parts per million, so it depends on your source you're looking at, but it's definitely much higher than the concentration of oxygen and nitrogen. And all three of these gases are non-polar. Oxygen, nitrogen, and carbon dioxide are all non-polar, which would suggest low solubility in the polar water solvent. But we do know that carbon dioxide undergoes the hydrolysis reaction with water, which is over here, and because it reacts with water to produce carbonic acid, that means it's highly soluble in water. Now, the low temperatures and the high pressures of the deep ocean, as we studied before, makes gases have a theoretically high solubility in the deep ocean. But the concentration of gases doesn't just depend on their solubility, it depends on their solubility and their availability. And there's a number of factors that mean that carbon dioxide and oxygen have different availability in the deep ocean, and therefore different concentration in the deep ocean. Just a little note over the side, you might be wondering why, even though nitrogen makes up more of the atmosphere than oxygen does, why their concentration in the ocean at the surface are roughly the same, and I'm pretty sure that's because oxygen is produced in the ocean by photosynthesis, whereas nitrogen is not. So nitrogen only dissolves, whereas oxygen dissolves and is produced by photosynthesis. But let's look at oxygen concentration. Oxygen concentration follows this curve here, this darker coloured curve. Just be aware the oxygen concentration scale is down the bottom here, and that means oxygen concentration goes from about 4 parts per million at the surface down to a minimum almost 0 parts per million, maybe up to about 2 parts per million in the deep ocean. And the reason why it's so high at the surface is because of mixing with the waves, the atmosphere mixing with the surface of the ocean due to wave mixing, but also photosynthesis actually makes oxygen in the surface of the ocean. But that only occurs for the first 100-150 metres, because that means after that light doesn't penetrate anymore, and therefore oxygen concentration drops quite quickly with depth, because now you have no photosynthesis, but you've still got respiration and decomposition processes consuming oxygen. So in this region here, you've stopped photosynthesis, but respiration and decomposition are still consuming oxygen. And it drops to very low values as respiration and decomposition use up a lot of the available oxygen. You do get a small rise in oxygen concentration in the deep ocean due to cold ocean currents that carry cold oxygenated water from the poles to the deep ocean. Carbon dioxide concentration, note it's always much higher than the oxygen concentration. Carbon dioxide is this dotted line here, but the carbon dioxide scale is up here. And note it goes between 45 and over 50 parts per million, so it's much, much higher in concentration than oxygen, but they've been drawn on the same graph, so without looking at the scales you might think they're comparable, but carbon dioxide is incredibly much more concentrated than oxygen in the ocean. At the surface, despite you've got wave mixing with the atmosphere, at the surface the carbon dioxide concentration is the lowest due to photosynthesis in the first 150 metres of the ocean using up the carbon dioxide. the carbon dioxide concentration rises sharply at about 150 meters, and that's for the exact opposite reason why oxygen drops. Respiration processes produce carbon dioxide, and also decomposition processes can produce carbon dioxide, and they're ongoing even though photosynthesis is stopped, and therefore the carbon dioxide concentration increases. And the carbon dioxide concentration continues to steadily rise in the deep ocean because you do have some decomposition processes taking place, but you've also got exoskeleton dissolution. At the surface, we've got some exoskeleton formation, such as things like crabs and shellfish and coral, taking in carbon dioxide or carbonate ions to make their exoskeletons. They can then dissolve in the deep ocean, which actually kicks up the carbon dioxide concentration. So that's the gases in the ocean. So overall, deep ocean corrosion predictions. We've just said that there is slightly less salinity, but that really has a negligible impact. But we know the deep ocean oxygen concentration is much less than air, and the deep ocean oxygen concentration is less than the dissolved oxygen at the surface. We know oxygen is the oxidant for rusting, and then that was predicted in the deep ocean because of these low oxygen concentrations that there will be slow rates of corrosion. In addition, the temperature of the deep, not the depth ocean, is less than the surface. Decreasing temperatures decrease the average energy of particles, so less particles have energy greater than activation energy for a given reaction, thus rate of corrosion was predicted to be low. And there's just a reminder of those diagrams you can draw if you're trying to explain how temperature affects rates of reaction. You've got T1 and T2. T2 is higher than T1. For a given activation energy, there are more particles at T2, the higher temperature, that have energy greater than the activation energy, therefore the reaction rate will increase. Let's move on. But what actually did they observe when they saw the deep ocean corrosion? Well, one of the most famous wrecks they found in the deep ocean was the Titanic, and despite the fact that it sank in 1912 and discovered in 1985, which is only about 70 years, it was heavily corroded despite predictions. It was covered in long rust flows called rusticles, named that after icicles. It also had flakes of different corrosion products all over the place as well. So you got rusticles here, and you've got flaky corrosion products here. The rusticles in particular contain bacterial colonies, and from last count they've found 27 separate species of bacteria that live inside rusticles, and lots of iron corrosion products such as iron oxide hydroxide, iron oxide magnetite, and flakes of iron sulfide. Elsewhere on the shipwreck, you got iron, silver, copper, also lead sulfide corrosion products were found. And at current rates, based on the rate of corrosion at the moment, it's predicted that the Titanic will be completely rusted away and just a rust stain in about 20 years. So what was causing this excess corrosion? And one of the first things they realised was there was something called sulfate-reducing bacteria. In the deep ocean, far from photosynthetic light sources and in anaerobic environments where cellular respiration is impossible, microorganisms have evolved to find alternative sources of energy. And Sporovibrio desulfuricurans is one example. This is a sulfate-reducing bacteria that reduces sulfate ions for energy. And the electrons required for the reduction come from the oxidation of iron, and hence these bacteria can accelerate corrosion of iron. That iron 2 plus then reacts with a range of species in the ocean to produce the rustical corrosion products. So you've got these ions react with the hydrogen sulfide produced from the sulfate reducing bacteria to produce iron sulfides. They can react with water to produce iron hydroxides. Then there's other species of bacteria in the ocean called iron oxidizing bacteria, and they can oxidize iron 2 plus to iron 3 plus, and that turns that iron 2 hydroxide into things like that iron oxide hydroxide and magnetite as well. Don't forget a little saying for this reaction to remember it. Solo 8 is 2 sneakers, 4 water. That's something to remember for that one here. And just take a note before we go on to the next page. All these reactions with these iron ions are producing hydrogen ions, which means all these reactions to make these corrosion products actually increase the acidity around the shipwreck. And that's the other reason why we have increased corrosion rates in shipwrecks in the deep ocean, because you've got these things called acidic microenvironments with low pH or higher hydrogen ion concentration, and they cause accelerated corrosion. The reason why you've got acidic microenvironments are things like the hydrogen sulfide produced by sulfate-producing bacteria is a weak acid. Those iron corrosion products we talked about produce hydrogen ions. Verdigris on copper formation also produces hydrogen ions. The sulfur oxidizing bacteria and iron oxidizing bacteria that live in shipwrecks also produce hydrogen ions. The higher concentration of carbon dioxide can produce carbonic acid, which is a weak acid, and decomposition of organic material in anaerobic conditions also produces hydrogen ions. There's a whole lot of reasons why you might have increased hydrogen ions in a deep ocean shipwreck. So what are the effects? Well, hydrogen ions can directly oxidize metal in a metal plus acid goes to salt plus hydrogen reaction or mass reaction. So the iron reacts with hydrogen ions to produce iron ions plus hydrogen gas. Low pH conditions assist the sulfate-reducing bacteria to reduce their sulfate, therefore increasing the rate of corrosion of iron. And also, oxygen is a stronger oxidant in acidic conditions, as shown by these two half equations. The E naught of 1.23 in acidic conditions compared to 0.04 in neutral and basic conditions. So that's the end of that section. I think our next focus will be on ozone CFCs, or indicators and esters.